Hi, this is Mrs. Villette, and I'm going to show you a problem having to do with arc length, revolutions per minute or revolutions per second, and angular and linear speed. So this is a diagram taken from a bike racing website, and what it shows is the crank, which is what the pedal is attached to, a chain that is connecting that crank to a rear cog or one of the gears on the bike. It's also showing that the velocity of the chain stays constant. We've also got the label of the radius for the chain ring and the radius of the cog. And then we have these other things, the omega of the cassette is this part, and the omega of the chain ring. The omega is going to be the speed, the angular speed of these different things. So we're going to suppose that the crank gear, which is attached to the pedals, has a radius of 12 inches, while the rear cog has a radius of 4 inches. If we're pedaling at 2.5 revolutions per second on a bike with 26-inch diameter tires, how fast will you go? So the first thing that we need to figure out is how fast the chain is moving. We know how fast this crank is moving, 2.5 revolutions per second, but we don't know how fast this rear cog is moving because that's what's actually going to make the tires go. So the tires are attached back here, and our pedal is attached right there. So there is a shortcut that we could take, and that is to take the radius of the crank, 12 inches, divided by the radius of the rear cog, 4 inches, to get that it's a ratio of 3:1. We know that the larger one is moving at 2.5 revolutions per 1 second, and if we just triple that, we get that the rear is moving at 7.5 revolutions per second. Now this should make some sense because this big crank ring is, or the chain ring is what they're calling it, is 3 times as big as the smaller one. So the smaller one should make 3 times as many rotations for every 1 rotation that the large one goes. Now I can show you how to argue this with arc length, or if you're okay with a shortcut, just take the shortcut. So if we look at the circumference of the chain ring, we would say the circumference is 2 pi times the radius of 12 inches, or 24 pi inches. Now we use the fact that it's going to move 24 pi inches per 1 revolution, and that it is going 2.5 revolutions per 1 second. This tells me that the linear speed of both the chain and any point on the exterior of the wheel is just those two numbers multiplied together, and that gives me units of inches per second. And 60 pi. So 60 pi inches per second is the linear speed of the chain. If I now take that linear speed of the chain, so that's what is being called up here the velocity of the chain. So if I take that number, the linear speed of the chain, that number stays the same on the rear cog. So 60 pi inches per second on the rear cog. If I want to figure out how many revolutions per second the rear cog is going, I already have the seconds here. I want to get revolutions in the numerator. So put it there. But I need to be multiplying by something that's actually a number that relates to this rear cog. I can figure out how many revolutions there are per inch. In fact, there is 1 revolution per 2 pi times 4 inches. This is, of course, just the circumference of the rear cog. Now notice, inches cancel, I get the revolutions per second as desired, pi cancels, and then 60 divided by 8, if we actually do that, we get 7.5. So that's why the shortcut works the way that it does. Now we need to actually answer the question. So if we are on a bike with 26-inch diameter tires, how fast will you go? Okay, so in a simplified sense, we've got the rear tire here, and we know that it has a diameter of 26 inches or a radius of 13 inches. And then we've got that cog attached to the chain, and we know that this is going 7.5 revolutions per second. So whatever the rear cog is doing in revolutions per second, so is the tire. So we will take 7.5 revolutions per second, and we just need to figure out how that revolutions per second translates into a linear speed. A linear speed should have units of like feet per second, or in this case I think we can get it to inches per second. We want to end up with inches on the top. We want the revolutions to cancel. We know that one revolution of this wheel is 2 pi times 13 inches. So now I just multiply 7.5 multiplied by 2 times pi times 13. And I get about 612.6 inches per second. That's not a number that you would usually tell somebody about how fast a bicycle would go. So let's go ahead and do a conversion on that to get miles per hour. So my goal over here is miles per hour. So first step is maybe the easy thing is to get rid of the seconds. There are 3,600 seconds per 1 hour. The 3,600 is just 60 times 60, so 60 seconds per minute, 60 minutes per hour. That gets our seconds gone and our hours that we want. Now I'm going to convert the inches into miles. There are 12 inches per 1 foot. Notice I'm always putting the units I want to cancel in the bottom, the units I want to keep in the top. That gets me into feet, and now I know that there are 5,280 feet in 1 mile. Feet cancel, I end up with miles per hour. Now I just go ahead and do 612.6 multiplied by 3,600 divided by, and I need to do the 12 times 5,280 in parentheses. Okay, and that works out to be about 34.8 miles per hour, which is pretty fast for a bicycle. Okay, so let's think about some of the general techniques here. One of the general techniques is that you're going to need to find the circumference of either the gears or the wheels. So circumference equals 2 pi times the radius, or circumference equals pi times the diameter. The next general principle is that you're going to be using unit conversions. And let's say you have unit 1 over unit B, and you want to end up with different units, like unit 2 over unit A. You need to multiply by something that will just take care of converting the unit 1 to unit 2. So let's say you knew how many unit 1s there were per unit 2. For example, this could be 12 inches per 1 foot. That will get your units to cancel so that you end up with the units you want. Now you're going to need a separate unit conversion to convert the unit B's to unit A's. I wanted the unit B's to cancel, so I put them on the top, and now I end up with unit 2 over unit A. Now you're going to use just the regular conversion factors that you know, like 12 inches is 1 foot, or 5,280 feet is 1 mile. 60 minutes is 1 hour, etc. So those are the conversion factors you're going to use. Other times we will need to convert an angular speed to a linear speed. So let's say you had an angular speed that was in revolutions per minute. So let's say you had 5 revolutions per minute. The first thing that you'd want to do is rewrite that as a fraction. 5 revolutions per 1 minute. We need to multiply by something that is going to end up giving me a linear speed. Now, I still want this minutes because a linear speed still is divided by time. But I'm going to multiply by something, 1 revolution per however many inches or feet or whatever. But basically, whatever is going to go up here is going to be the circumference of your circle. And that should give you a linear speed because your circumference will be in terms of inches or feet or whatever the measurement of your circle's radius is. So for an angular speed to a linear speed, take the revolutions per minute, multiply it by the circumference per 1 revolution. Now if they gave you the angular speed in terms of radians per minute or degrees per minute, so let's say that you went 30 degrees per second and you wanted to convert that to a linear speed. We would need to multiply by something that says there are 360 degrees per 1 revolution. So that gets me to revolutions per second, and then I do 1 revolution per circumference of the circle. You could just shorten this procedure. Notice the revolutions are going to cancel to a circumference per 360 degrees. Same idea if this was radians. If this was radians, you would have done 2 pi radians, but this should have also been in radians. Now let's say you wanted to go the other way. Let's say you wanted to convert a linear speed to an angular speed. It's not going to be much different. So let's say we had 30 inches per second. Again, I'm writing it as a fraction. So if I have 30 inches per second and I want to end up with an angular speed, it's probably easiest to get to revolutions first. You're going to figure out what the circumference is in inches, and that takes 1 revolution. So that would give you an answer that is revolutions per second. Now, if they then wanted you to get radians per second, then you would say, well, 1 revolution is 2 pi radians. Or if they wanted you to get degrees, you would say 360 degrees is 1 revolution of a circle. So really, the underlying relationship that we keep using over and over again is this one right here, 1 revolution per circumference. So our fundamental relation that we keep on using is we take the circumference per 1 revolution or 1 revolution per circumference. That is a unit fraction that we used in all of these examples.